All right, welcome to video 10, applications of the first derivative. This will be a part one to the video. There's a total of 3 parts. Um, it's really just because this lesson and this section is fairly long, so I want to kind of split it up so it makes it easier for y'all to digest, but also when you're writing problems for an assessment or you're trying to go back and look at things, it'll be easier to find them, and the problems will be a little bit more focused. So when you see the practice problems, I'll actually list like problems 1 through whatever is for part 1, part 2 is this, and blah blah blah. All right, so just to get into it, part 1 is probably the easiest one. It's also one that might be a little bit more familiar because part 1 deals with determining the intervals of increasing or decreasing. All right, and so we'll start with this application problem and kind of start with more of an analysis kind of problem. And it says this, according to a study by the U.S. Department of Energy and the Shell Development Company, a typical car's fuel economy as a function of its speed is described by this graph below. Essentially, what we're looking at is because we're talking about fuel economy as a function, we're essentially talking about its miles per gallon. So it's a fuel efficiency and how well it consumes gallons of gas. And this is all essentially based off, or at least one relationship that we can base off, is how quickly you're driving. Because it actually turns out that the faster you drive, the more efficient your car is in using its gasoline. But there is a limitation to that. And so when you look at the graph, essentially, really just what kind of observations do you see in terms of the graph? All right, well, in terms of just what we've been talking about, if you are noticing, even in terms of the figure description here, I could describe kind of the relationship for this by talking about how the miles per gallon increases as my speed increases, but it only increases up to roughly about 40 to 45 miles per hour, where now my miles per gallon actually begins to decrease in terms of efficiency as my speeds get greater and greater and greater and greater. So the faster you go, the less you'll lose in efficiency. And so we can kind of notice that there's an optimal speed here in terms of efficiency. But for now, we really just want to kind of focus on this idea of when we're looking at a function and we're looking at an equation, how do we describe when something is increasing versus how do I describe something when it is decreasing? All right, and so I have a general definition here, and this involves just looking at basic functions. And so this is a very mathematical definition. And so I'll kind of break down this as we go along. So a function f is increasing on an interval from a to b if for every 2 numbers x1 and x2 in that interval, f of x1 is less than f of x2 whenever we choose x1 to be less than x2. So let me give you a basic example for this. A basic function that we could look at would be something like f of x is equal to x. All right, and we know that this function is a line, it is linear, and you would describe this function as always increasing. So let's choose a specific interval. This would be the equivalent of my interval from a to b. So let's choose an interval from 1 to 5. And then what I'm going to do is, according to this definition, I would pick 2 numbers in this interval. So let's say x1 was equal to 2, and let's say x2 was equal to, say, 3. Well, then notice, because x1 is less than x2, that if I was to do f of x1, which is f of 2, and I found f of x2, which is asking for f at 3, plugging 2 in, the answer would just be 2. Plugging 3 in, the answer is just 3. Well, 2 is less than 3, so that means f of 2 is less than f of 3, which means f of x1 is less than f of x2. So essentially what it's saying is that at this initial y value, the next one is always going to be greater than. It's always going to be higher. And so we say that this function is increasing over this interval if this is true no matter the x1, x2 that you pick, so long as that your x1 is less than that. So when we say that a function f is decreasing on an interval from a to b, if for every 2 numbers x1 and x2 in that interval, we know that we are decreasing if each next y value is decreasing or less than the previous one, as long as that's the direction that we're looking at, if x1 is less than x2. So in other words, notice this part right here is talking about the y values. So if I'm increasing, then the next y value should obviously be greater than. And if I'm decreasing, the next y value should be obviously less than. But it's this part that's probably the most important because it dictates the direction of the graph and how we read it. Now, you know that we look at a graph and we read a graph left to right. Well, why do we do that? Well, we do that because that's the standard. And so that means, how do I tell somebody to read it from left to right? Well, I tell somebody that if you were to choose an x1 and then choose an x2, I want to make sure that I'm looking at it like this and not like this, where it's in reverse. Because if I was to reverse it, I'd be reading it from right to left. And something that may be increasing from right to left, it's now decreasing. And so it really, really matters how we look at our function and how we're visualizing the graph. All right, and so that's what this definition is referring to. We're not going to deal a ton with it, so you don't have to worry too much about doing exactly what I just did. Instead, we're going to focus on this idea, which is we say that f is increasing at a number c if there exists an interval from a to b containing that number such that f is increasing on that interval. So essentially, let's look at this visually, and we'll talk about how we can find this algebraically. Let's just say we looked at the first quadrant. So I'm just going to kind of draw a basic graph. And let's say my graph did something like this. And I said, all right, let's pick A to be right here at the beginning, and let's pick B to be right here at the end. So these are my x values. So I'll get rid of these lines so it's not confusing. So here's A to B. Now, I think visually we could all agree that this graph is increasing on this interval. Based on the definition we just looked at, as I go from left to right and I keep picking x values, moving to the right, the y values keep getting greater and greater and greater and greater. Therefore, we can say that we're increasing. All right, well, the next thing that I want to do is I want to pick this number c that is in this interval. So let's let c be somewhere in between. So let's let c be right here. So I'm going to go up to my graph, and here is f of c. All right, and so I can say that f is increasing at this point right here, so long as f is increasing over this entire interval. Excuse me. Well, I want to try and define this a little bit differently. And the way that I want to define it is using calculus and using this idea of tangent lines. All right, if I was to draw the tangent line for this function f at this point c, the tangent line would look something like this. Again, this is going to be a very rough drawing. So something like this. Remember that the tangent line essentially represents how the function is changing at a moment, specifically the slope of that tangent line. Well, if we're finding the slope of the tangent line, I'm looking at its rate of change. And if my function is increasing, it doesn't matter where I pick c, this tangent line will always have a positive slope, right? It's always going to be increasing as a slope because my function itself is increasing. Its rate of change is going to be positive. So my slope will be positive. Well, in calculus, we call the slope of the tangent line, we call a rate of change as marginal or as the derivative, meaning that f prime at c is going to be positive. It's going to be greater than 0. And this is the connection that we have to calculus with these ideas, is that when I want to talk about increasing, what we're looking for and what we're looking at is this definition, that f prime of that number, that y value at the derivative, the output there at the derivative, is going to be greater than 0, because this implies that the slope is positive, meaning that it has a increasing tangent line, an increasing graph. All right, well, if that's what we say for increasing, then if we flipped this and said, okay, we say that f is decreasing now, so we're focusing on kind of the opposite. Well, we say that it's decreasing on a number c if there exists an interval from a to b containing that number such that f is decreasing on the interval. So if I was to go through and do this visually again, and I was to draw kind of a first quadrant here, and I'll kind of extend this a little bit. and I was to draw a graph that I know is decreasing, so starting from left to right, it falls like this. Well, I know this is decreasing over the interval from A to B. So if I was to pick a value C in here, again, let's just say I picked right here. You could really pick anywhere in between these two values. And then I went up to my curve. I could essentially say this statement here that I know that f is decreasing at this number C. Well, if I was to draw the tangent line again, representing that change at that moment, this is going to be really hard because it's trying to fix it. I'll do it like right there. That's not bad. If I draw the tangent line there, remember that the tangent line represents its rate of change, and its slope, if I'm decreasing, notice is falling. So the slope here has to be negative. Well, in terms of calculus, then, we can say that the derivative at C has to be negative. It's got to be less than 0 because the graph is then decreasing there. And so this will essentially kind of lead into our first theorem, which says this and kind of puts it all together. So this is theorem 1. It says that if f prime is positive, right? If the derivative is greater than 0 for every value in an interval, then f is increasing on that interval. So if I could go through and I could show for every value in between a and b that this is true, that f prime is positive, then I can say that I'm increasing on that interval because its derivative, the slopes, its rate of change is all positive. Well, then the counter would be true, right? If the derivative is negative for every value in an interval, then I can say that f is decreasing because I know its tangent line has to be falling. It's this kind of imagery. All right, so if I know stuff about the first derivative, then we know stuff about the original function, specifically right now, whether that function is increasing and going up or going down. Well, increasing implies positive, decreasing implies negative. So what happens if you're at exactly 0, right? So if f prime is equal to 0 for every value of x in an interval, then f itself is constant on that interval. In other words, the y values are flatlining. There is no change. The graph is not going up. The graph is not going down. We're staying along the same horizontal. Well, the third one that I kind of want to add on to this is essentially then saying, okay, well, what if f prime does not exist at a specific value? What does that imply then about my original function? So I'll say for every value of x in an interval from a to b, then f is a vertical line on a to b. Essentially, at that moment, the graph reaches a vertical tangent line, or its tangent line essentially just does not exist. So maybe even saying it's a vertical line isn't true because there's a couple different scenarios that we'll talk about. So I might actually kind of scratch that out because that's what you would imagine that it might be. All right, so we'll come back and we'll talk about this a little bit later. For now, we're just going to focus on these, but this idea here of where f prime doesn't exist will pop up. Okay, so let's actually dig into some problems, and let's see in terms of this first example, let's find the intervals where the function x squared is increasing and the interval where it is decreasing. All right, and so we know that if I want to find increasing and decreasing in calculus, this means that I want to go through and find the derivative. So I want to find f prime. All right, so we find f prime by doing the power rule. So the derivative of x squared is 2x. And then I want to look at this equation and analyze it. And essentially, I'm looking for where is this derivative positive and where is this derivative negative, right? Where is this going to give me greater than 0 versus where is it going to give me less than 0? Well, looking at 2x, I know that if I plug in a positive value, this is going to give me a positive output. Versus if I plug in a negative value, I'm going to get a negative output. So to get f prime of x greater than 0, I need to plug in values where x is greater than 0 for 2x. And so I can say that, and I'll write the full answer in a minute. If I'm looking for where is f prime going to be negative, then like we just discussed, x needs to be less than 0. And so then I can state, in terms of my final answers, f of x is increasing on the interval from 0 to infinity. And I know that the original function is decreasing on the interval from negative infinity to 0. So this is my final answer right here. These are my intervals. All right, now this is pretty hard to do, especially when we get into more complex functions in terms of just looking at the derivative and essentially just saying, okay, well, I just know this or I just know this. So another technique that we do is once you go through and you find the derivative, let's go through and actually set it equal to 0. Because at this moment, the derivative is neither positive nor negative. So therefore, it has to be positive or negative everywhere else. So I'm essentially finding this moment where it's neither. So then I can figure out where it is, positive or negative. So 2x is equal to 0. Well, solving this by dividing by 2, we would get x is equal to 0. Notice that was the breakpoint here. And so then the second step is to use a number line. And so I'm going to draw my number line. And what I'm going to do is I'm going to put this point here where I know that the derivative is 0. And then I'm going to pick test values to the left and right, -1 and +1. And I want to plug these values into the derivative. And I'm checking to see if the response is going to be positive or if the response is negative. So for example, if you take -1 and I plug this into the derivative, I would get a -2 as a final answer, aka this would be negative overall. If I was to plug in +1, I would get 2, or just positive, because that's all I care about. So in other words, what that's telling me is that 0 is breaking it up, and that means the derivative is negative from negative infinity to 0, and I'm positive from 0 to infinity. And that's how I can get my answers. F is increasing, and then F is decreasing. So the number line's a really neat, orderly way to do it. We just have to use test values to do it. All right, so if you're looking for determining and steps and things like that, then I've got this for you right here. It says determine the intervals where a function is increasing or decreasing. Find all values of x for which f prime is equal to 0 or f prime is discontinuous. And then identify the open intervals determined by these numbers. That's okay using the number line. Select a test number C in each interval found and determine the sign of f prime on that interval. And so again, using a number line is probably one of the easiest ways to go through and kind of organize your work. All right, so let me show you how that works in example 2, and I've got 2 more examples for this part 1. All right, so determine the intervals where the function is increasing and where it is decreasing. So context-wise, because I'm looking for increasing and decreasing, then I know that I need to first find the derivative of the original function, right? So the first derivative deals with increase, decrease. All right, so I'm going to derive this. So I get 3x squared minus 6x minus 24, and the derivative of 32 would be 0. All right, now the next step is I need to go through and set this equal to 0. I need to find those breakpoints. And so that means that I need to go through and I need to factor this because I'm trying to solve for a quadratic. All right, the first step I'm going to look for is any kind of GCFs. So I can factor out a 3 to make my life a little bit easier. And then I'm going to factor this quadratic. What multiplies to give me -8 adds to give me -2. So that's going to be x minus 4 and x plus 2. And then I'm going to apply the zero product property. This would tell me that x minus 4 has to be equal to 0 or x plus 2 has to be equal to 0, giving me x is 4 and x is -2. These are going to be my breakpoints, my dividers on my interval. And so now I'm going to go through and set that up. So the second step is to use a number line. So I'm going to put in, here's -2, here is 4. I'm going to try to exaggerate it as much as I can to kind of show the division. And so I have 3 intervals here where my function can be increasing or decreasing. All right, I have, let's pick a test number here, so -3. I have in between -2 and 4, so the easiest number to pick there is 0. And then I have 4 to infinity. Easiest number to pick there would be something like 5. and I'm going to take these values, these test values, and I'm going to plug them back into the derivative. Specifically, I'm going to plug back into the factored form of the derivative here. And the reason why I'm going to do that is in terms of an algebra trick here, otherwise you could use a calculator and just plug and chug. But remember that I don't care about what the derivative value is, I just care about the sign of that value. So for example, again, if the derivative is 3 times x minus 4 times x plus 2, and I was to plug negative 3 in, this would give me 3 out front, which is positive. If I plug negative 3 into here, this would be negative 3 minus 4. Well, that results negative. If I plug negative 3 into here, that's going to give me negative 3 plus 2. Well, that result is still negative. And so then all I got to do is look at, well, what happens when I multiply a positive times a negative times a negative? Well, this result will always be positive, and that's how I can get my sign for each interval. You can use a table. I normally just continue using the number line. It's just completely how you want to approach the problem. I'll do this again. Let's say if I wanted to plug in 0 now. So I'm going to kind of get rid of these. All right, if I plug in 0, well, this number is still just 3, so that's positive. If I plug in 0 here, this is going to give me a negative result. If I plug in 0 here, that's going to give me positive. Well, positive times a negative times a positive is negative. So that interval is negative. Plugging in 5, you'll get positive. And so if you notice, the signs just kind of flip-flop, positive to negative to positive. And so now I can actually state my answer. I know that f of x is increasing everywhere that the first derivative is positive. Those intervals are negative infinity to negative 2, union 4 to infinity, because it's one of these two intervals. And then I know that f of x is decreasing where f prime is negative, and that occurs in the middle between negative 2 and 4. Now notice I'm not using brackets here for these intervals, because at these values, again, the derivative is 0. It's neither positive nor negative, so it's not increasing or decreasing at those moments. So it's always going to be parentheses around those points, and we're looking at all the values in between. All right, you could graph this original function and take a look at what it looks like. Right here, though, we have a pretty basic idea that the graph should increase until I get to negative 2 as an x value, decrease till I get to 4 as an x value, and then increase from 4 on. And so the graph would essentially look something like that if you were to sketch it out. If you were to graph it out, it would look something like this as a basic sketch. All right, and so notice that gives me some pretty good information about what it looks like without actually graphing it and understanding some of the behavior. And that ultimately will be our goal. For now, again, we're just kind of focusing on the increasing and decreasing. All right, so let's take a look at example 3. Okay, so example 3 says, find the interval where the function f of x is equal to x to the 2/3 is increasing and the interval where it is decreasing. All right, now the difference between this one and the original problem is that in the original problem, we could find the zeros, right? We could take the derivative and set it equal to 0. Now this one, that's not actually going to happen. Instead, we're going to find out that the derivative is actually undefined at a specific x value. And it's that undefined part that will split up my interval and create an increasing and decreasing. So let's dig into that. So number one, my first step here is I'm just going to take the derivative. So I'm going to find f prime. Well, using the power rule, the 2/3 comes to the front. And I subtract 1 from that. So this will be negative 1/3 as a power. And then I'm setting this equal to 0. And when I set this equal to 0, or I'm trying to solve this kind of scenario here, I really need to remember what happens when I have a negative power. So recall that a negative power would flip this to the denominator. And so this would essentially give me 2/3 x to the 1/3 is equal to 0. And when you have a fraction like this, remember that there's no way that a fraction can be equal to 0 if there's no x up here. right? The x being down here, there's no number you could plug in where this would hold true. So there's no solution to this. Instead, notice because the x is in the denominator, in this kind of statement here, x cannot be 0. We have this defining factor. So when I go to my number line, I have to respect that. And this is what in the steps is referring to, and I'll put a dotted, like a dashed line here to represent it. Essentially, it's like a vertical asymptote. It means that the derivative doesn't exist here. Well, that's good for us in terms of answering the question, because again, what I care about is whether the function is increasing or decreasing, not whether it's undefined or 0. So where it's undefined, we'll still split this number line up. So I have to respect that. So when you get a fraction in terms of your derivative, look for something like this and remember that this is an answer. All right, and so I need to go through and pick two test numbers. So let's pick -1 and +1. And then I'm going to plug this back into the derivative, and I'm looking and checking for the sign. All right, so if you take -1 and you plug it back into the derivative, you would get a negative result. If you plugged in 1, you would get a positive result, giving us the answer that we're looking for, that f of x is increasing, where f prime is positive, so that would be 0 to infinity, and f of x is decreasing, where f prime is negative, aka negative infinity to 0. Again, just to point this out, that although even this is undefined, still it alternated from negative to positive. And I don't want you to get stuck in the trap that this is always going to be true in terms of this alternation. And this is what example 4 is going to point out. So the purpose of number 4 is to dig into, well, does the function always alternate between increasing and decreasing? Like, will it always be something like up, down, up, down, up, down? And this next one's not. All right, so find the intervals where the function f of x is equal to x plus 1 over x is increasing and where it is decreasing. All right, now, before I derive this, anytime I have, personally, something that looks like this, 1 over x, I want to rewrite it into a power rule. So this would be x plus x to the -1. So in other words, I want to take x and flip it to the numerator by negating its power. At this point, then this is just two power rules. And so I'm going to go through and find the derivative. Here's my step 1. So the derivative of x is 1. The derivative of x to the -1, the -1 comes down. Take 1 away from the power. And so the derivative is essentially 1 minus 1 over x squared. And then I want to set this equal to 0 and solve this. Now immediately, just like last time, don't miss this because I did initially when I was working this problem. See how I have an x in the denominator? So immediately, I'm going to go ahead and kind of make a note and say that x cannot be 0 because I need to make sure I put that in my number line when I go back through. All right, so to solve this, I'm going to add the 1 over x squared over. So this will be 1 is equal to 1 over x squared. I'm solving for x, so I need to get it out of the denominator by multiplying both sides by x squared. So we'll get rid of it here. So I get x squared is equal to 1. Taking a square root, I'll get plus or minus 1. And so there are my other two values for x. All right, now I'm going to go through and draw a number line. And now I need to mark any of these places where the derivative is 0 and anywhere where the derivative is undefined. All right, so I'm going to mark -1, then I'm going to mark 0. Again, I'll use a dotted line here just to help represent that. And then my other value, 1 here. All right, and now I need to pick some test numbers. So -2 would be from the interval -infinity to -1. Then I've got the interval in between -1 and 0, so like -0.5. I'll choose +0.5 on the other side, and then 2 on the other side of that. All right, and again, I'm going to plug this into the derivative. And I'm going to go back, and I'm always going to use essentially the first expression, this one here, where it's been rewritten, but hasn't been solved for, things haven't been simplified. All right, so if I was to plug in -2, again, you could do this in a calculator, you could do this by hand. Negative 2 squared would give me 1 over 4. So this is essentially saying 1 minus a quarter. Well, that's going to be positive. So there's that. Extend that line there. All right, if I was to plug in negative a half, this would be 1 over negative a half squared, which is 1 over 1 quarter, or 4. So it's 1 minus 4, so that's result's going to be negative. If I plug in 0.5, you'd find that this result is also negative. And if I plug in 2, you would get this result is actually positive. And so when it comes time to write my answer for this, I'll get that f is increasing on the intervals of negative infinity to negative 1, because I'm going all the way to this line here. But I'm also increasing from 1 to infinity, so union 1 to infinity. I know that f is decreasing on the interval from negative 1 to 0 and from 0 to 1. I do not represent that as one big interval because how that's undefined there in the middle. All right, so this would be my final answer here for this last example in the final part. To show you this, let me graph the original function so you can kind of see that this is actually accurate. So make sure you write this down because I'm just going to type in the original function. I'm going to go to Desmos, and again, I want to type in the x plus 1 over x, and let's take a look at its graph and see if it is true in terms of the information we just found. So let's do x plus 1 over x. And so this is what the graph looks like. And so if you notice here, this graph increases. Let's see if I can use my pencil. I'm trying to click on there we go. And I'll put it in projector mode so it'll be easier to see. If you notice, this graph will increase until I get to negative 1, which is where this little dot here is located. But then after that, the graph continues to decrease until I get to 0. Well, notice the break here at 0. There's a vertical asymptote there. And so if I pick up my pencil and I come up to the top of the graph, notice the graph is falling until I get to 1. And then it's increasing from that point on, from 1 to infinity. And so I can say that this graph is increasing until 1, or excuse me, increasing until negative 1, and then increasing from 1 to infinity. And I'm decreasing from negative 1 to 0, and from 0 to 1. All right, so hopefully this kind of makes sense. We are getting a little bit more technical, a little bit more mathy. So let me just pull this back up. And so I just want to leave you with the conclusion of the theorem, which is this. Biggest thing that I need you to take away is that if the derivative is positive, that tells me that f is increasing. If the derivative is negative, it tells me that the function is decreasing. And if the derivative is equal to 0, then my function is constant. I've hit a peak or a valley, or it's perfectly horizontal. The tricky part is what does it look like when the derivative does not exist, and we'll talk about that. The function can either be a vertical line, or we'll see that it hits a corner, or the graph goes vertical for the briefest of moments, and then continues on. There's some unique functions that do that. All right, so that's it for part 1. Take a look at the practice problems if you want to focus just on this. There will only be one discussion post over this entire video, so don't worry about having to make 3 different ones for this, for each part. That is not a requirement. And then feel free to move on to part 2 if you feel ready. Thank you.